Hello and welcome to this video. So this video is part of the class Introduction to Artificial Intelligence and Machine Learning for Engineers. So today what we are going to talk about in this video is a follow-up of the last video. The last video we saw a theoretical introduction to artificial neural networks and their architecture and the role of the activation function, and how to select the optimal number of neurons in the hidden layers. So today what we are going to see is how, in practice, how to use Matlab to train an artificial neural network model. So for this, we are going to, as usual, illustrate this with a given dataset. So in this case, we have a dataset that contains some information about different forest fires. And so it contains some information about different observation of fires, and the information that we have is for different temperature, different atmospheric humidity, and different wind speed. We have the corresponding risk of fires, so those information were recorded at different time of the year. Both in winter and summer. And the goal of this video will be to train a model that can predict the risk of fire in terms of the average temperature, in terms of the relative humidity, and in terms of the speed of the wind. So let's start with just loading the data as usual. So let's import the data. So we are going to redo the same thing that we usually do. So we are going to load the data in a matrix like this. And so far the data are just stored in a CSV file. So we are going to read this CSV file and import this into a matrix. Okay. So then what we are going to do is, if you look at this data, what we have in this data set is as follows. So we have three different columns that corresponds to the input. The first one is the temperature. The second one is the relative humidity in percentage. The first one is the temperature in degrees Celsius. And the last one is the wind velocity, the speed of the wind in kilometer per hours. And the fourth one is the output. This is what we want to predict. This is a risk of fire in percentage. So this is the chance that a fire starts in a given forest in percentage. So what we are going to do is to select within this matrix. We are going to select the three first columns. So we're going to take all the lines and select column 1 to 3, and we are going to put that into X. So this is going to be our inputs, and then we are going to put the output of the model, which we are going to take all the lines and only take the fourth column. This is going to be the output of the model. And we are going to just store the number of observations that we have. That can always be useful to have this variable. Okay, so once you have done this, as usual, it's always a good idea to start by visualizing the data. So just to have an idea of the data that we have. So let's start by visualizing, doing some basic visualization of the data. So for this, there is two things we can do. First, we can plot some histograms. So let's do that. So let's plot some histogram. So let's start with plotting an histogram with the output of the model. So let's see what we have. So the output here is the risk of fire. Oops, let me run this first. Okay, so this output is the risk of fire. So here we see that the risk of fire goes between 0 to 100%. So that's a percentage. In this case, we see that there is much more data that have a very low risk of fire. Like in many cases, the risk of fire is very low, but in a few cases, you have a pretty high risk of fire that goes up to 100%. So in this case, when you have a very skewed data like this, a skewed distribution where you have a lot of data that are centered at very low values and just a few rare events like this, it's often a good idea to take the log of this output, to calculate the log of this value. Why? Because if you calculate the log of this value, which we are going to do, so let me just create a new variable. So we are going to normalize the features and transform the output. Okay, so let's just do that. So what I'm going to do here is to avoid having an output variable that is so centered around 0 and only a few rare events around very high risk of fires. What I'm going to do is to create a new output value that is going to be the log, and typically we will take the log of 1 plus the output. So we transform the output y into the log of 1 plus y. We usually put the 1 plus to avoid since y can be 0, we don't want to take the log of 0. That would cause a not a number error. So we need to add plus 1 just to make sure that we don't have the risk of taking the log of 0. So now I'm creating this new output that is the log of the initial output, and if I look at what the histogram of this new output looks like now we have something that is much more well-behaved distribution. That this distribution can go between 0 and about 5. And it's much more uniformly distributed. Not quite uniformly distributed, but still it's less centered around very low values as compared to the initial output. So now let's take a look at the features. So let's take a look first at the distribution of the first column. The first column is the temperature. So if we look at the temperature, so it looks like the temperature goes between 0 to 40 degrees Celsius. In this case, it's pretty uniformly distributed. Let's look at the second feature, which is the relative humidity. Relative humidity goes between 0 to 100 in this case. 100% relative humidity is what you get in a very humid environment. And close to 0% relative humidity is what you would get in a very desertic area. And then we have on the third column the wind speed, which in this case it's pretty uniformly distributed as well, and it goes between a speed of 0 kilometer per hour up to 40 kilometer per hour. Okay, another thing that is also useful to do is to plot the relationship between the input and the output. In this case, we have several inputs. We have 3 different inputs, so we cannot plot directly the relationship between all the inputs and the output of the model. So we need to look at the input one by one to just see if there is some correlation between each of the input and the output. So let's first plot what we get when we plot the risk of fire as a function of the temperature. So I'm going to plot on the x value the temperature and on the y axis the risk of fire. Okay, so let me put it like this. Okay, so if we plot this, so we get some kind of scatter points like this that is very, it's very hard to see a trend, because here we are only plotting the output as a function of one of the input. But we know that there is more than one input, so all those inputs can vary. So here we are plotting as a function of one of the input, but the other input are also free to vary throughout the dataset. So necessarily we are not capturing all the variability. We are plotting only one of the possible causes that can change the risk of fire. So for a given temperature. So this first input here is the temperature. If we look at a temperature of 30 degrees Celsius, we see that the risk of fire can change a lot. And this is because the other variables can also change. So for some of those points, you will have a high wind. For some of the other, you will have a low wind. For some of the point, you will have a high relative humidity. For some other point, you will have a low relative humidity. So like here, it's hard to directly see the relationship between the input and the output because all the inputs can change at the same time. That being said, if we look carefully, we kind of see a linear increase that the higher the temperature, the more you have a risk of fire. But of course, it's very noisy, and this is why we want to train the machine learning model. If the relationship between risk of fire and temperature was very obvious, then we would not need to train a machine learning model. So let's take a look at the other variables. So okay, so on the second variable, this is going to be the relative humidity. So here we have, again, a pretty noisy relationship, but we nevertheless find that the higher the relative humidity, the more humid the weather is, the lower the risk of fire. And when the relative humidity becomes very low, this is when you have the most risk of fire. When it's very dry weather, this is when the risk of fire increases a lot. So we kind of have an inverse correlation here between the risk of fire and the relative humidity. Let's take a look at the last feature that we have, which is the wind. And in this case, again, it's a pretty noisy relationship. It looks like the higher the speed of the wind, the more the risk of fire. But again, it's a pretty pretty noisy relationship because again, all the features are varying at the same time. Okay, so now we are going to do this transformation. So what we are going to do in addition to that, as usual, we are going to normalize all the inputs just to make sure that all the inputs have the same weight and to accelerate the training of the model. So we are going to normalize all the inputs between 0 and 1. So for this, we are going to take to do a loop on the 3 inputs, and we are going for each of those inputs. So for each input, we are going to remove the minimum value of this input. So we are going to remove the minimum value so that this input will now start at 0. We are going to divide by the range of this input. So we're going to divide by the range being the maximum value of this input minus the minimum value of this input. And then we are going to store this new normalized input into, let's call it x2. So we are going to store this into x2. x2 will be the normalized version of x, where now x2 will now go between 0 and 1. Okay, so let's just make sure that everything went well. So this is y2. y2 is the log transformation of the output. Okay, which looks good. The output, we don't need to normalize it between 0 and 1 in this case. We just care about the features, about the input. So let's look at all the inputs one by one just to make sure everything went well. So this is the temperature. The normalized version of the temperature is now going between 0 and 1. Let's see what else we have. We have the relative humidity. Same thing, it's now between 0 and 1. In this case, the relative humidity used to go between 0 to 100%. So we could have just divided by 100 to have something that goes between 0 and 1. And let's look at the third one. The third one is the wind speed, wind velocity, which in this case also goes between 0 and 1. Okay, so everything looks good. So now we have the new output y2. We have the normalized version of the input. Again, if you look, if we plot the relationship between the variable, the input variable and the output variable, let's take an example now to see what it looks like. If I plot the relationship between the normalized version of the temperature and the log of the risk of fire, let's see what it looks like now. So let's plot it like this. So if I look at this, it still looks like it's nothing very much helping so far. So we still have a very noisy relationship, no clear relationship between the input and the output. If we look at the others, same thing. This is the role of the relative humidity. We kind of see an inverse relationship, but it's not very clear. And if we look at the role of the wind velocity, same thing, very unclear. So here in this case, it looks like a linear regression model would not work well. For example, if you look at the relationship between the input and the output, it looks like it's an inverse relationship, or it could be a quadratic relationship. But in this case, it's pretty hard to assume that there would be a linear relationship between the features of these data sets and the output observation. So in this case, what we are going to do is we could do like we have done last time to generate some new features, to engineer some new features, especially if we had some understanding on how the risk of fire would depend on the temperature, on the relative humidity, and on the wind velocity. We could engineer new features that are going to be very correlated to the risk of fire. But here what we are going to do is let the artificial neural network create its own feature directly. And we are going to use the artificial neural network to find what are the feature that the model wants to create, how it wants to combine the inputs of the model to create some new features in the hidden layer. And we are going to let the model find the best nonlinear way of interpolating, of mapping the input to the output. So we are going to see, to take this example, to train an artificial neural network. Okay, so for this, what we are going to do is to use the function in Matlab that can be used to train an artificial neural network. So let's do this. So now we're going to train the artificial neural network. Okay, so in Matlab, you have a few functions that can be used to train some artificial neural network. So for this, like the function that we are going to use is the function fitnet. So the function fitnet, it can take different input, but the main input that we are going to worry about in this video is just the number of neurons in the hidden layer. So here what we are going to do is first to train a simple neural network. So this neural network will have three inputs. Those are going to be the three inputs of this model: the temperature, relative humidity, and speed velocity, or the normalized version of those variables. It will have one output, which is going to be the risk of fire in percentage, or the log of the risk of fire, more accurately. And then it is going to have some neurons in the hidden layer. And those neurons in the hidden layers will be the new features that the model is creating. It's going to combine the input features in certain ways to create some new features in the hidden layers. And then those new features are used to predict the output of the model. So for this, we are just going to use one single hidden layer. So we're just going to do a shallow model, not a deep learning model, just one single hidden layer as a simplified start. And the only thing that we are going to look at is the effect of the number of neurons in the hidden layer. So this fitnet function is going to create the artificial neural network, the architecture of the artificial neural network. And in this case, the only parameter that we are going to worry about is the number of the neurons in the hidden layers. So we are going to provide a variable that is going to be the hidden layer size, and this variable is going to be the number of neurons in the hidden layer. So let's start, for example, with 10 neurons in the hidden layer. So we're going to start with this architecture with 3 neurons in the input layer, 10 neurons in the hidden layer, and only 1 neuron in the output layer, corresponding to the single output of this model. So this function fitnet is going to create the network, and then we are going to store this network into the object net, like this. And then we need to provide a few details to the way this network is going to be trained. So the first thing we need to tell is what is the size that we want to use for the training set, and what is the size that we want to use for the validation set. So remember that we use the training set to train the model, so to make the model learn from the data, and we use the validation set to optimize the hyperparameter, like the architecture of the model or the internal parameters of this model. In theory, you could also be using a test set in addition of the training set, the validation set. You could use a test set. Usually, the reason you would use a test set is to see how well the model is performing on totally unknown data. So the difference between the validation set and the test set in this case is as follows. You start with the training set. The training set is what you use to train the model. So the model is only going to see the data from the training set and to try to optimize the parameters of the model. The parameters of the model in the case of an artificial neural network are the weights of the connection between the neurons and the value of the bias. So the first thing that the network is going to do is, by being exposed to the data in the training set, it's going to try to learn optimal values for the parameter, like the weight of the model, the weights of the connection between the neurons. Then it's going to use the validation set to optimize the hyperparameters of the model, to try to optimize the internal parameters of the model. In this case, we are not talking about the weights. We are talking about the internal parameters of the model. Like in the case of a lasso, for example, you have a regularization parameter. Here it's the same. In artificial neural network, you have different parameters about the model itself. Those are not weight parameters. Those are not parameters that will affect the relationship between input and output. Those are some internals parameters that you can tune when you train the model. So, for example, one of the hyperparameter in artificial neural network that is very important is the number of neurons in the hidden layer and the number of hidden layers. Those are very important hyperparameters. So we are going to use the validation set to optimize those hyperparameters, to find the best possible values for the hyperparameter that minimizes the error for the validation set. And then once we have chosen the best value for the hyperparameters, then in addition to that, if we want to see how well the model is performing for totally unknown data, then we are going to define, in addition to the training set, in addition to the validation set, we are going to again keep a fraction of the data set that we are going to use as a test set. And the reason that we define another fraction of the data set as the test set is that we don't want to reuse the validation set to test how well the model is predicting fully unknown data sets, because when you use the validation set, you already used those data in the validation set to optimize the hyperparameter. So you tuned the hyperparameter of the model specifically to reproduce well this validation set. So then if you use this validation set to see how well the model is doing, it's not a fully fair test because you have already optimized the hyperparameter to match with this validation set. So if you want a fully fair test to evaluate how well the model is doing with some data that the model has never seen, some data for which you haven't adjusted the hyperparameters, then you would have a training set first, maybe 50% of the data. Then you would have a validation set to tune the hyperparameters, maybe 20% of the data. And then you would have a test set, maybe about 30% of the data. So in this case, since we don't have so much data points, we have only 500 data points in this data set, we are not going to use the test set. The test set is something that is very important, especially when you have a lot of points. But in this case, we just don't have enough points to really afford to have a good test set. So we are just going to use one training set to train the model and one validation set to optimize the hyperparameter. So the first thing that we are going to say is to define how many, what's the fraction of the data points in the data sets that we want to use to train the model, the training set, and what's the fraction that we want to use for the validation set. So for this, we are going to use this, we are going to define this attribute of the object net. So we are going to say that net dot divide param train. So we are going to fix the parameter of this neural network, and we are going to say that the train ratio is going to be 70%. Okay, so we're going to say in this case that the training ratio for this network is going to be 70%. Then we are going to do the same for the validation set. So we're going to define the validation ratio with this parameter val ratio, and we are going to say that this is going to be 30%. And then we are going to do the same for the test set. So the test set that I just mentioned, in this case, we're just going to say 0% for the test set. Okay, and then once we have done this, we can start to train the model. Okay, so there would be a lot of other possible parameters that you can change, like the type of activation function, or the types of learning method that you want to use to optimize the model, but we are not going to worry about this. It's not going to make a big effect for these types of data sets. So we're going to just use those default parameters, and we are going to focus only on the number of neurons in the hidden layer. So then to train this network, so far the network has not been trained. It has just been defined. We have just defined how many neurons in the hidden layer. We have just defined the fraction of training set and validation set. Now we're going to train it. For this, we're going to use the train function. This train function is going to take as input first the network that we want to train. That's going to be the first thing. And then we need to put the input of the model. The input of the model in this case is going to be x2, so the normalized version of the input. And we are going to put then the output of the model. The output of the model is going to be y2, which is the log transformation of the output. Okay, and so this training function, what it's going to give us is two things. So we're going to get two things as an output of this function. First, we are going to get the network itself. So this is going to be the trained artificial neural network. So once it is trained, then you can use it to calculate the output value of you can calculate the output for any value of the input. Once you have trained the model that can map your three variables, temperature, relative humidity, wind velocity, and once you have the model that can use those input to predict the risk of fire, then your new network becomes some kind of a function that can take any value for the input and give you a prediction in turn as an output of the risk of fire. So the train function is going to give us back this complex function, this network that we can use to make some prediction. And it's also going to give us some information about the training of the network and about its performance. Okay, so if we just do this, this is going to cause an error message, but let's just run it first to have an idea of what is going on. So here, if we run this, we find that it's telling us that the input and the target have different number of samples. So if we look at the size of those inputs that we just provided, so the size of x2, it has 500 lines and 3 columns. Those are the 500 observations that we have, and 3 are the 3 different inputs. And when we take y2, the size of y2 is 501. 500 is again the 500 observation that we have, and in this case there is only one output. So it looks like that this should work, but for some reason in Matlab, for the train function, for training an artificial network, Matlab is expecting that the input and the output will not be provided as columned vectors, so not as different vectors, different columns that contains the different variables, but as different lines. So for example, if we look at x2, it contains the 3 columns that contains the 3 input features. What Matlab wants in this case is 3 lines. So what we need to do is very simple. We just need to take the transpose of this matrix. So rather than having x2, we are going to provide x2 prime like this, so that it's going to take the transpose of this matrix and just going to provide 3 lines. If we look at the size of x2, you have 500 lines and 3 columns. If you look at the transpose of this, now you have 3 columns and 500 lines. Okay, so we are just going to create a new version of the input. So let's define the transpose of x, which is going to be x2 transposed, and let's do the same for the output. So let's define the yt, which is going to be the transpose of the output. And now what we are going to do is, this is what we are going to provide to the model. We are going to train the model to learn how to map xt to yt. Okay, so let me just delete those things and restart to make sure we have the right size for the features. Okay. Okay, so there is still oh, I have forgotten to take the transpose of this thing. Okay, so now it's training the model. So when you run the train function in Matlab, it's going to show you this kind of graphical interface. So it's pretty useful because first on the top you see the network. So here you can see that the network has 3 input neurons, that it has 10 neurons in the hidden layer. Here it's showing you the architecture of those neurons. So here we have the weights. The weights are the weights of the connection between the neurons of the input and the neurons of the hidden layer. There is the bias here. What it's doing is that it's taking the product of the input times the weight. It's summing all those terms plus the bias, then it feeds that to the sigmoid. In this case, the activation function is a sigmoid. You can change this. In this case, we are just going to keep a sigmoid, but it might be a better choice to use a rectified linear unit. So a ReLU function would probably be a better choice. And then all those 10 neurons of the hidden layer are connected with some weights to the output, and then this output is going to predict the output of the model. You have only one neuron in this case that is just going to use those features that are created in the hidden layer. So here, the way this network works is that you start with those 3 features in the input layers, and those input layers features are going to be transformed into 10 different features. Those are the 10 neurons of the hidden layer. The model will just create on its own 10 different new features that are going to be obtained by combining in different ways those inputs, those 3 neurons of the input layers. And those 10 new features are then going to be used to predict the output. So what the model is going to be doing during the training is to optimize the value of the weights W and the value of the bias. This is what is optimized during the training. So here you have a few plots that you can do. That I will let you take a look at this, but there is a few interesting information that you can get, and some information about the performance of the model. So okay, so let's see what this model look like when we try to let's try to look at the performance of this model. So let's look at the performance of the ANN network. Okay, so let's see. So if you want to look at the performance of the ANN network, what we will want to do is exactly the same thing as what we do for the other model. We will want to calculate the RMSE, the root mean square error, for the training set and for the validation set. And then we will want to see the data, to plot the data. So we will see how to do this. Okay, so the first thing is that if you want to calculate the root mean square, the root mean square is going to be the difference between the true output and the predicted output by the model. So if we want to do this, now that we have we have this variable, this object net. So net is the network. This is the trained artificial neural network. Now this artificial neural network can take any input and make some prediction. So the first thing that we are going to do is to compare the prediction of the model with the true values of the output for the training set, and then we are going to do this for the validation set as well. So for this, we need to make sure that we are going to interrogate what this model net is predicting for the input of the training set, and then of the input of the test sets. So for this, we need to see what the model is predicting, but only for the lines that corresponds to the training set, and then only for the lines that corresponds to the validation set. So the way we can do this is to see. So I'm going to look at the predicted value y, the predicted output by the model for the training set. So let's see what the model is predicting for the training set. So if I want to do this, I'm going to use this new net function. So this net is the artificial neural network. So now we can just use net and provide to net the input. We provide the values of the features, and net is going to transform this feature into the output. So here what we want to do is to provide the value of the features for the training set. So for this, the features that we use to train the model, this is xt. So xt is the list of the 3 features that was used to train the model, but we don't want to provide all the xt. xt, this is the entire data set. We only want to provide the 70% that were used to train the model. We don't want to put the validation set at this point. So we only want to put certain lines of this xt, of this vector xt. And the lines that we are used to train the model, those 70% of the lines, they are stored in one of the attributes of this tr object here. If we look at this tr object, there is a lot of interesting information in this tr object. This tr object contains a lot of information about the architecture of the model, the parameters that we are used to train this model. It also contains what we will care is this. Those are the index of the lines of the dataset that were used for the training set. So here it used 350 of the points of the dataset. So those are the 70%. We started with 500 lines in the dataset. Out of those 500, it selected randomly 350. So this is going to be here the number of the lines, the index of the lines that we are using in the training set. And in this variables, we have the index of the 150 lines that are used for the validation set. So this is how we can figure out which lines were used for the training and which lines were used for the validation set. And the way you can have this is to use it to look at tr dot train index. If you look at this, it's giving you the number of all the lines. So here you have 2, 3, 4, 5. So it means that line number 1 is not here. So it means that line number 1, for example, was used in the validation set in this case. And then you have the other 350 lines that were used for the training set. And then if we look at the train for the validation, so we see that line number 1, line number 11, line number 15, those are the number of the lines that were used in the validation set. So now if we want to see, if we want to take only the value of the features for within the training set, what we are going to do is to take this variable xt. We are going to use all the features 1, 2, 3, and we are going to take only certain of the lines, which are going to be only the lines corresponding to the training set. So if we do this, now we are selecting only out of all the values xt of the datasets, we are only selecting those lines that corresponds to the training set. Okay, and then so we are selecting those features corresponding to the training set. We are transforming those features into the output by feeding that to the trained neural network. Okay, so great. And now, so this is going to be the predicted, this is going to be the value of the output that is predicted by the neural network. If we want to calculate the RMSE, we need to compare this to the true output values, like the true observation that were found in the datasets. So for this, we are going to define the white train true. This is the true value in the datasets. So in this case, this is what we had into YT. So this YT here, but again, we just need to take the lines that corresponds to the training set. So we're going to take the lines only corresponding to the training set to get only a subset of the dataset that correspond to the training set. And then once we have this, we can use this to calculate the MSE. So we can take the difference between the predicted values minus the true output of the datasets. We take now the square difference. Remember that we need to put point hat so that we can take the member by member square and not a vector product. Then we are going to, so this is the square error. And then we are going to take the average of all those squared error for all the observation. This is going to give us at this point the MSE, the mean squared error. If we want the RMSE, then we are going to take the square root of this mean square error. So this is going to give us the RMSE of the training set. So let's see what it gives. So here we find an RMSE of 0.77. At this point, it's hard to know if this is high or not high, because here what we are seeing is the RMSE of the predicted output. And the output that we are predicting at this point is not the percentage of the chance of fire, it's the log of 1 plus the chance of fire. So it's when you try to look at the log of the chance of fire, it's a little bit hard to understand what it means. So here, if we want to have an RMSE that we can understand, it would be better to reconvert the predicted value into the real chance of fire, the real percentage chance of fire. So here, if we take this Y train, the value that the model was trained to predict is the log of 1 plus the percentage of the chance of fire. So what we are going to do is to take the exponential of this. If we take the exponential of this, then now we have we take the exponential of the log of 1 plus the chance of fire. So now we have the 1 plus the chance of fire. So if we want just the chance of fire, we can just do minus 1. So now we have taken the exponential of the log, so we get the just 1 plus the chance of fire. We do minus 1, so we get the chance of fire. Okay, so we are going to do we can just do the same here, just to make it easy to have the true value. Here we could just simply use we could just simply use the original output that we had before the transformation, but let's just make it like this. Okay, and we are going to now, so it means that now we are going to calculate the model that that will be the value that will be calculated here will be the true chance of fire. So remember that in this case we define the log of 1 plus the chance of fire because it's a much more easy variable to predict, that is less skewed or less centered at very low chance of fire. But then it means that now that's the only thing that the model knows how to predict. The only thing that the model knows how to predict is the log of 1 plus the chance of fire. But that's not a problem. Like if you train the model to predict the log of the chance of fire, then all you have to do is to use the model, let the model make its prediction, and then you retake the exponential of the prediction. So as long as you can do a transformation that is reversible, you can transform the output into the log and then train your model based on this and then retake the exponential of your model. That's not a problem. You need to provide if you can make some mathematical transformation of the input or of the output that make it easier for the model to be trained, then it's a good idea. And then you can just do the inverse of this transformation to retransform back the output into its original value. Okay, so now if we do this, now we find that the model is predicting, has a RMSE, an error that is about 8. And now we can understand better the meaning, because now this 8 means that the model is making an error of about 8%. Like when I say 8%, I mean as compared to the chance of fire. The chance of fire is a number that goes between 0 to 100%, and we are predicting this with an accuracy of plus 8%. So in this case, that's a number that is easier to understand. So when I say 8%, I mean that that's the 8% chance of fire. It's not a plus minus 8% of the. It's not a percentage of the predicted value. It's just the predicted value itself is a percentage, and we have an uncertainty of the prediction that is plus minus 8, which in this case is a percentage. Okay, so we are going to do the same now for the validation set. So we are going to do exactly the same, but this time we are going to calculate the values that are predicted for the validation set. So we're going to select the values of the features for the validation set, feed them to the network so that it can make some prediction for this validation set, and then we are going to retake the exponential of the prediction -1 to reconvert that into a percentage chance of fire. And we are going to do the same thing. We are going to just calculate the subset of the dataset that corresponds to the validation set. So same thing, we take this gives you the number of the lines of the validation set, and we this is going to give us the portion of the data sets that corresponds to the validation set, and then we are going to retransform this by taking the exponential -1. Okay, and then same thing, we are going to calculate the RMSE by taking the square difference between the value that is predicted by the model for the validation set and the value that is the true value in the data sets for the output of the model. Okay, so let's see what we get. So here we find that there is an error of about 8% for the training set, and the error for the validation set is about 8.6%. So slightly higher, but here it looks pretty good. So we have an accuracy of about plus or minus 8%. The error of the training set is very similar to the error of the validation set, so that's a good sign. It means that the model is probably not overfitted. So what we are going to do now is to see if we can make this model better or at least if we can make sure we have chosen the right number of neurons in the hidden layer. So okay, that's gonna be the second thing. So what we are going to do simply here is just do a loop on different number of neurons, and we are going to train this model for different number of neurons, and we are going to then see what's the RMSE of the model for the validation set as a function of the number of neurons, and based on this select the optimal number of neurons that gives us the lowest RMSE for the validation set. Okay, so let's optimize the number of neurons in the hidden layer. Okay, so what we're going to do is we are going to do a loop like this by varying the number of neurons in the hidden layer, and we are going to do this between 1 and let's say between 60. We're going to try between all the combination between 1 neurons in the hidden layer and 16 neurons in the hidden layer. And then we are just going to retake this this entire thing here. We are going to put this here, and we are going to now retrain the model, but this time we are going to say that the number of neurons in the hidden layer is going to be I, where I is going to vary between 1 and 60. Now we are going to define the network. We are going to say that the fraction of training, validation, and test set are still the same. Now we trained the network here. So this is about defining the architecture of the ANN. So remember that defining the architecture for a neural network means that you are providing the number of hidden layers and the size of each layers. Here we are training the artificial neural network, and then what we are going to do is just to calculate the RMSE. So we're going to determine the error of the ANN. So for this, we can reuse those things here. So we are going to reuse exactly the same thing. So we are going to, in this case, we first calculate what this model is predicting for the training set. We are going to then take what it's predicting for the validation set. Then we're going to compare this with the true training set, the true value of the output for the training set. And we are going to then compare this with the true value for the validation set. Then here, so we calculate the first one here is the RMSE of the training set, and then the second one here is the RMSE of the test of the validation set. Okay, and then we are going to store those RMSE so that we can plot them later as a function of the number of neurons. So we're going to define this into a variable. This is going to be the RMSE of the training set as a function of this variable I, which is going to be the number of neurons in the hidden layer. And same thing, we are going to store the RMSE for the validation set as a function of y. Okay, so let's train all of those models. So here it's going to take a little bit of time because it's going to train all those 60 models with different number of neurons in the hidden layers. Here you can see that the number of neurons here is gradually increasing. So every time it trains a new model, here it shows us the new architecture. So here we see gradually that the number of neurons in the hidden layer, there is only one hidden layer so far, but the number of neurons is gradually increasing. And what we expect is that when you have too few neurons in the hidden layer, then we expect that the model might be underfitted, too simple. But when there is too many neurons in the hidden layer, possibly the model might become overfitted. So based on this, so now we can try to plot the outcome and select the optimal number of neurons in the hidden layer. Okay, so for this, what we are going to do is to plot two things. We are going to plot for each number of neurons. So the number of neurons goes between 1 and 60. We are going to plot the RMSE of the training set that we calculated here. So we're going to plot for each of those training set score. Here we're going to calculate the RMSE of the training set for each of the 60 cases. Then we are going to hold down and we are going to plot on the same plot the accuracy of the validation set. So we're going to calculate the RMSE of the validation set for each of the cases for all the number of neurons in the hidden layer between 1 and 60. Okay, so let's see what we get. So, okay, so here what we have is in blue, we have the RMSE of the training set as a function of the number of neurons in the hidden layer. And here in orange, we have the RMSE of the validation set as a function of neurons, of the number of neurons in the hidden layer. So what we can see is we can see the typical features of underfitted and overfitted model. So when you have very few number of hidden layer of neurons in the hidden layers, then the model is underfitted. At this time, when the model is underfitted, the error becomes high both for the training set and the validation set. It means that at this point the model is too simple, so it will have a high bias and it will have pretty much the same error in the validation set than in the training set. But it's gonna be a pretty poor prediction just because the model is too simple and cannot properly interpolate the relationship between the input and the output. It doesn't have enough complexity to map the relationship between input and output. And then on the other hand, if you increase the number of neurons, then you make your model more and more complex. So here in blue, the RMSE of the training set decrease, and it just continue to decrease and then eventually reach a plateau. But when you add too many neurons in the hidden layer, then the RMSE of the validation set starts to increase again, which means that in this case, your model become overfitted. It's too complex, so it has a high variance. It doesn't generalize well for unknown data. So it predicts very well the training set, but it keeps the memory of the noise of the data sets, and it doesn't generalize well. It's overfitted, doesn't generalize well for unknown data. So in this case, the RMSE of the validation set starts to increase again because the model becomes overfitted. So you can see that having an overfitted model is a big issue. So it's not a good idea when you're trying an artificial neural network. It's not a good idea just to use a high number of neurons, because if you use too many neurons, then you will see very poor prediction by your model. More complex is not always better. In this case, it's actually probably better to use a model that is too simple rather than a model that is too complex. A model that is too complex will really not generalize well and will give you a pretty high error for the validation set. So based on this, now we can define what's the best architecture for this model. Here, the best architecture would be, you can see that when you see where the MSE or the RMSE of the validation set is minimum. And here in this case, this is when we have 7 neurons in the hidden layers. It is what is giving us the minimum value of the RMSE for the validation set. So this is the architecture that we are going to use in this case. So if we go back to the training of the model, so we are going to use 7 neurons in the hidden layer. That's the lucky number. So we are going to retrain this model with 7 neurons in the hidden layer, and then we are going to recalculate its performance, and you see it's a little bit better. So now we have RMSE of the training set of about 7%, and RMSE of the validation set that is around 6%. Here in this case, it turns out that the RMSE of the validation set is a little bit lower than the RMSE of the training set, which is usually not the case. Usually you should have a lower error for the training set, but here it's just because we are training only one model. If we train it again, we are going to get a different answer. So ideally you would need to train this model several times in order to have a more accurate estimation of the RMSE of the test set and of the training set and of the validation set. Ideally, you should train it several times with different split of the training and validation set to have a better overview of how well the model is interpolating the training set and how well it's generalizing to the validation set. So in addition to those RMSE, one thing that is good to see is to plot some prediction from the model. But here we cannot really plot the output as a function of the input, just because there is several input. Like it's a multi-dimensional model. There is 3 dimensions in the model, so we cannot plot make a plot with 3 dimensions. So for this, one useful plot that we can use in order to visualize what the model is doing is to predict to plot the predicted output by the model and to compare this with the true output. So this is what we do in the RMSE. When we do the RMSE, we calculate the mean square difference between the true output and the predicted output, but we can also make a plot of this thing by plotting the predicted output as a function of the true output. So let me show you what it looks like. So here we're going to visualize the prediction from the model. Okay, so and the way you can visualize the prediction even when you have several dimensions is to do the following. So we are going to plot, in this case, we are going to put on the x-axis the true output. So this is going to be the ground truth. This is going to be the true value of the output. So we are going to do this for the training set first. So we're going to put on the x-axis the true value for the output, the true chance of fire. And then we are going to put on the y-axis the value that is actually predicted by the model. So we're going to put on the y-axis the chance of fire that is predicted by the model. Okay, so let's see what this is giving us. So, and then we're going to first plot this. So if we look at this, now we have some points here. On the x-axis, this is the true chance of fire. And on the y-axis, this is the predicted chance of fire by the model. So if your model was perfect, what it would predict is that if the true chance of fire is 60%, your model would predict 60%. That's if the model was perfect. So it would predict exactly the same. For 100% chance of fire, it would predict 100% chance of fire. But because your model is not fully perfect, there is a little bit of variability. So to see how well the model is doing, it's useful to compare those predictions here with the line that corresponds to the diagonal here, the line that corresponds to y equal x. So let me draw this line. So first, so I'm going to hold down and then plot just a line that goes between 0 to 100. And this line is just going to be the line that corresponds to y equal x. So for every x, you get exactly the same value of y. So let's see what we get with this. Okay, so if I plot this, so this line here in orange correspond to the case where the model, what you would get with a perfect model. For a given true predicted value, this y equal x line gives you what would be the corresponding predicted value that your model should predict if it was perfect. And what the way you can see if your model is doing well is to see for all the prediction is to see how far are they from this line. If you have a prediction that is very far away from this line, then it means that those points here, for example, are not very well predicted. They are far away. The true value is close to 55% of fire, but actually what the model is predicting is more like something like 27 or 25, 27, something like this. So the more the points is far away from this y equal x line, the less good your model is. So this is one way to see how well your model is doing, to see if there is more error for the model at high risk of fire or low risk of fire, etc. So we can also add on this plot the how well the model is doing for the validation set, the value that we are not used to train the model. So we're going to put this with a different symbol like this. Okay, so in this case here, so in blue we have those are the how well the model can interpolate, and in orange this corresponds to the prediction of the model to the validation set. So to the point that we are not included during the training of the model. So those points tells us how well the model is generalizing. So it looks like it's working pretty well. Like for example, if you take here this point, it means that we had a point in the data set that you had a true chance of fire of about maybe 80% and 86%, and the prediction was 70%. So it's a pretty reasonable prediction. So we see that probably most of the error in this case is at very low chance of fire. Like it's hard for the model to properly predict that. But for all the other cases, the prediction is never very far away from the ideal case that corresponds to this y equal x line. Okay. So now let's just see what the model would look like if it was not properly optimized. So let's just see, for example, if you take a very extreme case, if you only take one neurons in the hidden layer. So let's just see what the model would now look like. So if you do this, you see that the RMSE now is becoming higher. Instead of having an error of about 7%, now you have an error of 10 and 12%. So you can see here that when you look at this plot, on average, the points now are further away from this y equal x line. So it means that the model is, in this case, is underfitted. The way you can see that the model is underfitted is because, like, even for the points of the training set, the blue point, even the points of the training set are pretty far away from the ideal prediction y equal x. So this tells you that the model does not even properly interpolate the relationship between input and output within the training set, which tells you that in this case it is most likely underfitted. And then let's just take a very extreme case, like if we take, for example, 100 neurons in the hidden layer, which is going to be a pretty overfitted model. Let's see what it looks like. So now we see that when you look at the training set accuracy, it's not too bad, it's 9%, but the problem mostly comes from the validation set. The model does not generalize well. It predicts a very high error for the validation set. So like the way you can see that here is that you have for the validation set, the points are pretty far away from the optimal prediction. So let's try to make it very extreme. Like if we put 1,000 neurons in the hidden layer. So in this case, it's really a model that's going to be very heavily. Oops, I think I stopped it before training. So it's going to be a model that is going to be very heavily overfitted. In this case, it takes quite a bit of time to train because there is a lot of weights to train in this case. Okay, so if we look, like in this case, it's very very extreme because, like, if you look at the training set error is very very low, but the test set, the validation set error is very high. Let's just see what it looks like. Yeah, so here it's almost impossible to see. Like the error is so big for the validation set that it's almost impossible to see. I think I forgot to refresh this plot. So I was showing you always the same plot actually. So let me just restart. So if you have only one neurons in the hidden layer, then you should have a very underfitted model. So like the error is high both for the training set and the validation set. So let's just replot this. Okay, yeah, so sorry, I didn't update this plot. So this is the kind of plot that you have when the model is underfitted. Like the error is obviously very high, both for the validation set in red in this case, and for the training set in blue. Like this is how you see underfitted model where even the training set in blue is not well predicted. Let's go back to, let's take 60 neurons in the training sets. So for this, we expect to have an overfitted. So this one, okay, is going to be marginally overfitted. So let's just try a little bit more, 100, to make it more obviously overfitted. Okay, so this one is going to be a better illustration. So here you can see that this is a good signature of an overfitted model, because the data point in blue correspond to the training set. The data point in blue are pretty close to the y equal x line, so the training set is pretty well fitted. But the problem here is that the model doesn't generalize well. It generalizes very poorly. So the data for the validation set are pretty high from the y equal x line. So this is the manifestation of an overfitted model. It predicts well the training set, very well the training set, but very poorly the validation set. Here you have an uncertainty of an RMSE of 21%. Okay, and in this case, again, let me show you again what you get for in this case, the best architecture, which is for 7 neurons in the hidden layer. This is the case where you have almost the same accuracy, like for the training set and for the test set, they are predicted both with an accuracy of about 7%, plus minus 7%, which in this case is a good signature that your model is not underfitted and not overfitted, that it's not biased, and that it generalizes well enough. Okay, so in this case, we're not going to go any further than that, but there would be some way to improve this model even further, maybe by adding some additional layers. Like here, we have only used one hidden layer. If you wanted to add more than one hidden layer, all you would need to do is to change this line here. We can just give it a quick try. Like if you want to have one first hidden layer with 7 neurons and maybe then a second hidden layer with 4 neurons, you would define it like this, and now you would get a new artificial neural network that still has the 3 inputs: a first hidden layer with 7 neurons, then a second hidden layer with 4 neurons, and still the output layer with only 1 neuron. Let's just see what it looks like, but in this case, it doesn't help. Like it's actually making the error worse, which means that for this case, adding some additional hidden layer does not seem to help. Okay, so in this case, it's probably not a good idea. But in this case, you could still, if you wanted to have 3 layers, you could just do it like this. In this case, you would have 3 hidden layers with 7 neurons each, and in this case that would make the model more complex, but that would only probably very marginally help increase the accuracy, because in this case we have only 500 data points, so we cannot really afford to have a very deep model with a lot of hidden layers. So probably here a single hidden layer is probably a good guess for this model. Okay, so just to summarize what we have done. So again, first thing is always to import the data. Then it's always a good idea to visualize the data. Remember that it's by visualizing the data that we found out that it would probably be a good choice to transform the output into the log of the outputs. Okay, so if you don't visualize the data, then you cannot see if some inputs or some output would deserve to be transformed, mathematically transformed one way or the other. Then we normalized the features. It's always a good idea to normalize the features so that they have all the same range. And in this case, we also transformed the output into the log of the output to make sure that you have a more well-behaved distribution from the output. And then you can just try to optimize the hyperparameter of your artificial neural network. In this case, we just focus on only one thing, which is the number of neurons in the hidden layer. In this case, we can just do a grid search when we just vary all those, the number of the neurons in the hidden layer, like we just try them all. Here we can afford this because like we don't have so much data, so it's very fast to train this artificial neural network. So we can just try all the possible architectures and just see the one that works the best. In real life, when you have millions or billions of data points, then maybe you cannot afford this kind of grid search. So you will have to find some other strategies on how to optimize the hyperparameter. But in our case, it's just fine to try them all and to select the one that appears to be the best balance between the model not being underfitted and not being overfitted, and to find the best number of neurons that minimizes the RMSE of the validation set. So this is, in this case, an illustration of how you can use Matlab to parameterize those artificial neural network. If you want to use it yourself, you can start with this, but there is a lot of other options that we haven't covered in this video, like how to change the activation function, etc. In most of the cases, changing the activation function can impact the result, but might not necessarily have a very high impact, especially for the kind of data that we are dealing with in homeworks. But for more advanced research project, then probably you need to look in more the details of the different options to try to select properly the right activation function, the right number of epochs, the right fraction of training sets, validation set, and test set, the right number of neurons, the right number of layers, etc. So there is a lot of parameters that needs to be tuned if you really want to have the highest possible accuracy for the model. Okay, so that's it for today. Thank you for listening.